Good morning. So, on behalf of the graduate program in astronomy of the Observatório Nacional, be welcome to our special courses 2023. This is the edition number 25. So, since 1996, the Observatório Nacional has had these special courses dedicated to providing to students, the graduate students, and also postdocs, a broad overview in selected topics in different areas like astronomy, astrophysics, and cosmology. So each year we invite experts in different areas to give course in different fields of research. So this year we have the great honor to have the presence here of Dr. Rafaela Morganti, Dr. Noemi Pinilla, Dr. Cristina Chiappini, and also Dr. Carlos Martins, that will give a course remotely. Okay, so thank you very much for accepting our invitation to be a lecturer here in our special courses. And I have also to say thank you to many people, so I have a long list, so please be patient, okay? So I have to say thank you very much to the organizing committee, Dr. Jorge Carvano, Dr. Armando Bernoulli, Dr. Rodrigo Gonçalves, Dr. Ricardo Gando, Dr. Alberto Ardila, and also thank you to the DCOP, our Division of Education and Outreach, Dr. Josina Nascimento, Lorena, Rodrigo, and Vanessa. Also Luiz Henrique, who is very happy due to the victory of Fluminense. The DETIN, our IT division, especially Beethoven, who creates the school's webpage. Our secretaries, Gianni, Cristiane, Gisela, Amanda, and Tamiris. And also our director, Dr. Jailson Canis, for all the support. So without these people, the organization of this school would be impossible. Huh? Andrea, also Andrea, of course, yes, Andrea. So, and also thank you very much for your presence here, okay, because the CCE is made for you, okay? So let's enjoy your CCE and thank you very much, okay? So let's start our CCE. Oops. Okay, now I have to read this. So our first speaker is Dr. Cristina Chiappini. Dr. Chiappini is a senior researcher at AIP in Potsdam, Germany. She got her PhD in 1998 at the University of São Paulo and also CISA University in Trieste, Italy. Is that correct? Yeah. She was also a postdoc here at ONE. Researcher fellow at Columbia University, research astronomy at Trieste Observatory, and also at the Geneva Observatory. She has been awarded several prizes and received many special grants. She has more than 108 published papers with more than 25,000 citations. Her main research fields are on galactic archaeology, with a particular focus on the chemical and dynamical evolution of the structural components of the Milky Way, as well as on very metal-poor environments, stellar populations of the galactic bulge, and Milky Way accretion history. So here at DCCE, she'll give us a course entitled Galactic Archaeology in the Gaia Era. So Dr. Chiappini, thank you very much for accepting our invitation. Please take the floor.
Thank you very much for the presentation, for the introduction. I just excuse for the non-Portuguese speakers. I just want to say one word in Portuguese. Eu queria agradecer o convite por estar aqui. É muito legal voltar ao ON. Eu queria dedicar as minhas aulas a fazer uma homenagem aqui ao Márcio Maia, que não está mais aqui com a gente, mas que eu gostava muito, aqui do ON, e eu tô com um pouco de falta de ar, porque eu tô com um negócio no pulmão, então eu vou tentar falar com calma. Geralmente eu sou muito rápida e hoje eu tô lenta. Se vocês não entenderem alguma coisa, tiver pergunta no meio, pode fazer, porque a aula tá feita para ser relax. Eu vou começar, e eu vou falar inglês, obviamente, mas eu queria agradecer a todos por estarem aqui e fazer essa homenagem ao Márcio. Então, so the lecture title I put is Galactic Archaeology in the Gaia Era, and the reason is that Gaia has completely changed the way we work in the field of Milky Way, but not only, has changed also, have impact also in other fields. But of course, the main goal of Gaia was to map the Milky Way, to map the distance in the Milky Way, and so that we can really understand the distance of the stars, which is difficult to get, but also other parameters. And with that, construct this map, and this is what I'm going to show you in this course. We will have this map, and with this map, it's a multidimensional map where you have position, velocities, chemistry. We complement Gaia with other data sets, and with that, we can then understand how our galaxy formed, which were the most important event for the galaxy formation. That's the goal. So I have organized I will have this problem that when I look to the computer I need this, and when I look there I cannot use this. So you see me like this all the time. This is age problems. Okay, so I have organized the lecture. We have 4 lectures. So the first one, I'm going to give you a general view of how we are trying to do this map of the Milky Way, and how we need complementary information to make this happens, so that we can really get, is amazing, because you can have a level of detail that you cannot have in any other galaxy. And what we learn for the Milky Way, of course, applies to our understanding of our other galaxies as well. And another point important is that with the Milky Way, because we are here, we see stars individually, we can also see back in time, because the stars of different ages, different compositions, bring us back in time. So at some points, I will be discussing the universe 12 giga-years ago, depending on where I'm going, which stellar population I'm going. And at some point, I'm discussing the stellar composition today. And that's what the Milky Way gives you, this reference of time. So I have organized the first one to give you this view, how we have been combining Gaia with other data to get to these maps. The second is really using this information to understand the complex history of the Milky Way. It became very clear the Milky Way had impact with another galaxy right in the beginning of its existence. The Milky Way is forming inside out. The stars that are forming a region are moving to another region. So all this is happening, and it's complicated then to analyze the data, okay? But at the same time it's complicated, it's also a gift, because, for example, we have difficulty to get to the center of the galaxy, but you have stars that were forming the center of the galaxy and move here. So you end up, if you are able to find them, you end up having a way to tell detailed history of stars, chemistry, that were born very far away, that you would not get to observe them directly if you need to go there. You see, not yet. With ELT, in the future telescopes, you're going to get there. So the second lecture is more heavy. And the third one then, finally we can now have, is very recent, combining other information, we can get into the bulge of our galaxy. And when we are in the bulge of our galaxy, we have really a complexity of mixture of populations, and there is where a lot is going to happen in the next years, with other instrumental and telescopes and detectors and so on. A lot will happen in the near infrared, and we will get a lot into this area. So this is like, I finished with 2 lectures about the bulge, because the bulge connects to the disk, and because the stars move, you cannot understand the disk if you don't understand the bulge, and vice versa. So this is happening right now, and that's why I wanted to give you a lecture that really shows what's happening right now. And so that's why there are 2 lectures for the bulge, but the bulge finished with the future outlook. So that's how I think we're going to manage. I'll start with this picture, which is what I'm not going to talk. So this is an X-ray Rosetta picture of the galaxy. So here you see the map of the galaxy, and you see this, essentially what you're seeing is these bubbles. So why I'm showing this, because most of what I'm going to speak about here is about the stellar composition of the Milky Way. I'm not going to talk about the gas. So you can imagine that the stars are in the Milky Way, and that's the stars I'm using as fossil records to tell me the history. But in the middle of these stars there are gas, and there's a lot happening in the gas, and this is leaving some imprints. Some stuff you can see in the X-ray, this beautiful image that was a very recent, December 2020 came the Rosita, where my institute also has an important contribution. And you see this bubble coming from the inner region, which is most probably an outflow. And this is all happening in that central region that I'm interested. But I'm looking only to the stars. So every time we are thinking about something, you have to understand that there's a lot more happening, right? Another thing that is amazing, this is the galactic center. I'm not going to talk about this because this is gas. And this you see in radio. You have one of the lectures will be about radio in other galaxies. But this is amazing, the detail you get in radio when you look to the inner parts of the galaxy. And that's why you get these images that are amazing. For example, here around the Sagittarius A. And I have to mention that in the middle of the galaxy there is a black hole, right? That gave the Nobel Prize to Penrose, Gas, and Genzel in 2020. It was a Nobel Prize for the discovery. I mean, it was known that there was, but to see this way the black hole in the beginning, in the middle of our galaxy. Okay. So now you saw three things happening amazing in the center of our galaxy, which I'm not talking about, but you should be aware they are there. Now what I'm talking about is this. So this is Gaia. This is the Gaia EDR3. So there has been several releases of the Gaia data. Each release is, I mean, you work like crazy because you have to learn everything that's coming out, how to use this data and to transform it in what you need. And this is amazing because this looks like an image of the sky. You have, because you live here in Brazil, you can see the Magellanic Clouds. And then you have the disk of the galaxy and you have dust. So that's why you have these black things here. And where you see more stars, you have a concentration of stars towards the inner parts of the galaxy and the disk of the galaxy. And this image is not an image. This is what is nice. This is a number count of stars. This is stars. For each of these, Gaia has a color, a position, a proper motion, and a parallax with enormous precision. And that's what we're going to look. And so you have this. So this, for example, this pixel here is not a pixel, it's a globular cluster. So this is the level of detail that you have in an image. Like, it's not an image, it's just density of stars. Density of stars with this level of detail. So, why I told you that we can go back in time in such a way in the galaxy? So we have the gift here is the chemistry. And not because I am chemically biased, because I am a little bit, but it's because the chemical evolution, the aim of the chemical evolution, that means when the universe started, we had only hydrogen and helium, right? From the Big Bang. And later you build up the periodic table. So to the point that we are here talking. So the chemical evolution of the universe, how the universe builds its chemical elements, which then are restored. The stars are born, restore the chemical elements into the gas of the galaxy and form new generations of stars that have more chemical elements that, again, eject their gas from new generations. So this is the chemical evolution, right? How the elements are produced and increase in the galaxy. We can use this information, not only in our galaxy, but in our galaxy we have detailed chemical information. While in an external galaxy we have integrated chemical information. And then we can see in our galaxy chemistry and stars of different ages. Ages is a very difficult parameter to obtain, but we are getting more and more precise ages. And with different composition. So the different composition of stars of different age are bringing me to different epochs of our galaxy formation. And this is what is very beautiful. We have I put here a list of some foundations of this field, very important papers like Tinsley, Pageau, and so on. So, we have a very important parameter, not only for our galaxy, but for any galaxy we're studying, is star formation rate. And the star formation rate, which means the rate in which you're forming stars, gas is converted into stars. And this is changed if you have more gas. If you give more gas to the system, if you take out gas from the system. So this is intrinsically related to gas flows. Then you have the initial mass function. The initial mass function is a key parameter in any kind of, even if you do integrated stellar populations or in our galaxy. The initial mass function is the distribution of mass that the stars are born with. And we live in a universe where the IMF, as it called, initial mass function, is similar to a salpeter, which means that you have a lot more stars with low mass and very few stars with high mass. And the key here is that the stars of low mass die quickly. The stars of low mass live longer. And some are older than age of the universe, the ones that are below 0.8 the solar mass. And the massive stars that die and they restore. So this is giving us a very important information, which is time scale. We are going to use this, which is related to the lifetimes of the stars. So the IMF, so how many stars are formed per unit of time, what is their mass distribution, and then what time they live and die. And what do they produce? These are yields, stellar yields. When the star died, what is the star ejecting to the interstellar medium? It depends on the mass of the star. Okay? So, for example, I'll give you an example. Oxygen. Oxygen is mainly produced by type 2 supernova explosions. These stars live short time compared in the time scale of the galaxy. So that means that when the star formation is on, any galaxy that have an ongoing star formation is giving a lot of oxygen to the system. Other elements need time because they will come from low mass stars. So if I start the star formation today, I'm not going to find a lot of those elements produced by these low mass stars. Because today, if I'm starting from star today, I'm going to see oxygen, for example. No? And this is going to be a key thing during the whole thing. So what I'm saying is this. Different elements are made in different nucleosynthetic sites and therefore released to the interstellar medium on different time scales. And this is going to be what I'm going to be using here to interpret what is the history of our galaxy. But, there is a but. And it is in the but that most of the work is here, so I have to put the but. The models and conclusions that we can take from this information, they can be completely wrong due to the mix of stellar populations. And this will be clear by the end of my lectures. Because dynamical processes affect the distribution of the stars, which we call secular process and mergers, and also we have sometimes lack of sufficient information to disentangle this, and this can give you to non-univocal answers, even in the Milky Way. So what do I mean? I mean that when I study a sample of stars, let's say around us, in a local volume, as I told you in the beginning, many stars came from somewhere else and are here in this local volume. So if I interpret as everybody is here, and then try to trace a star formation history based on this data, I can go wrong. Because I didn't take into account that some stars were not formed in this volume, they came here. Another thing that can go wrong is that I got a merger, and the stars that I have here in a volume are not from the Milky Way. They were formed in a dwarf galaxy, and they are here. Can I figure them out? Because depending on the situation, they can be a lot. For example, if they are from Gaia Enceladus was a galaxy that collided with ours that was now seen, and I'm going to show you, discovered by Gaia. It was a merger with our galaxy that was important, happened 10 giga-years ago, and the debris are around. Another one is Sagittarius. Sagittarius having several passages with our galaxy, and has not only left some stars that we see in the trail and the leading arm, but also can trigger star formation. So you see, things get, so the but here is the whole thing. It's going to be in the but. So I have to show you this is one basic chemical evolution clock that you use also for other galaxies. And now with JWST, we are trying to also measure this at very high redshift for other galaxies. So in this axis here, you have oxygen over iron, an abundance ratio. And here you have iron. The important here is the scale. It's a logarithmic scale. right? When you have this bracket. So solar is 0 here. Solar here. Solar here. So the sun is here. Okay? These curves have to cross solar. -1 is then 1/10 of the solar metallicity. 1/100, 1/1000, the solar metallicity. And today, we have stars up to 1/-6, okay, or -5. So, to find the very metal poor stars is a whole work on its own, because most of the stars around us are piling here. Okay, so if I just go out and measure the stars here, I'm going to get a bunch of stars here. And if I want to learn something about those stars here, I have to look for them in a different way. Because they are like the agulha no palheiro. Esqueci como é que fala em inglês. Fala aí. Needle in a haystack. Exactly. So this is the scale. And here is again logarithm. So 0.3 is like a factor of 2. No? So 0.5 means somebody that is enhanced in oxygen over iron with respect to solar, because it's above. Of my lectures, you have to understand this. And if you didn't understand, you have to ask. Oxygen over iron here in the past is above solar. Yeah? Okay, now I have a plateau and suddenly things go down in these plots. What happened? At some point, this plateau is telling me oxygen and iron were being produced, more or less similarly. At some point, more iron came into the game than oxygen, right? What happened? So it turns out that has to do with the nucleosynthetic site of iron. Type 2 supernova can make some iron. And the quantity between oxygen and iron made in core collapse supernova give you the plateau. At some point, the type 1a supernova kick in. What are them? They are binary systems that have an explosion after some time, because one star, intermediate mass stars, has to throw matter to the other one. This goes above this goes above a Chandrasekhar mass, and then there is an explosion. And what happened is that you produce a lot of iron in this thing. And then you have to remember, so these are the ones that are giving the iron, 3 times more iron than a type 2 supernova can produce. But then, why are they coming at some point? Because IMF, they are from low and intermediate mass stars. So they have a larger number of stars, but they need time to die. They have longer mass. And so it turns out that there is a time delay to happen, this iron release. And this is what is telling here. At the solar vicinity, let's see the curve for our solar vicinity around us. The curve more or less is this. If we put the stars that are 1/10 the metallicity of the sun, we will find that they have high oxygen over iron. When we get back to the sun, it's down. It means that the time has passed, that the type 1a had time to die. And this here, this inversion, is more or less 1 gigayear. So this plot here is not linear. It's 1 gigayear for the solar system to get here, and then 13 or 12 gigayears to get the rest. Okay? And then you got here, you are sun, 4.5 gigayears ago. And then you have the rest of the evolution, the last 4.5 gigayears ago, which not much happens at this position. So this is not at all linear. But you understand it. And now you see here bulges plus ellipticals and Magellanic clouds and a dwarf galaxy. Why is this different place? Because now, imagine you are in the bulge on an elliptical galaxy. The star formation period of time is very high compared to the one you have in our plateau here. Now I have difficulties. I would have called this halo, but now halo is going to see is more complex. So what happened? I formed so many stars per unit of time that I managed to increase in iron just from the type 2 supernova. Even though they don't make a lot of iron, I could increase here down in X only with type 2 supernova because I was making a lot. And then at some point, the type 1A kick in, it goes down again. But I walk more in metallicity and then I drop. Now I'm going to Magellanic Clouds. Magellanic Clouds has a star formation that is slowly, is going, it's not the same efficiency as the Milky Way. So here, it took so long that right in the beginning, already at low metallicities, I'm already having the type 1A. So the plateau starts being corrosive before and then go down. Now I have a dwarf spheroidal galaxy. In the top of this, I have a gas, an outflow. I throw stuff out. Again, I can make changes in this plot due to outflows or due to other things. Now you say, what happens if I change the IMF? The IMF gives me the number of stars that are massive versus no massive, and because inside the massive range, which goes from 8 solar mass or 10 solar mass up to whatever mass you believe is the top mass, let's say 100, there is a distribution. The stars between 8 and 100 do not throw the same quantities of oxygen. There is a distribution. And so if I make a mean by the IMF, how many they are throwing, it turns out that is around 0.5, which the cell I use. But if I had an IMF that's more top-heavy, this thing could go a bit up here or could go up. So this is sensitive to IMF. And this is sensitive to star formation efficiency. You see? So this plot has a lot, and that's why we are after this plot. But this is just one chemistry. It's like the easiest one, alpha over iron plot. You're going to hear about this all the time, but you can use several others. But the problem is it's more difficult to measure. You can use neutron capture elements. You can use carbon, nitrogen that gives you a lot of information. You can use a lot of other things, but you have to understand this plot to then jump to the next. Is this clear, this plot? Anybody has? Okay. Okay, so I have no idea of the time here because we started late, so I don't know. I have spoke 25 minutes. Okay, fine. So let me just talk because we have here people that are not Milky Way, right? So let me just briefly talk about this. We have different challenges when we are working on the Milky Way and when we work on other galaxies. And so for galaxies, you have the challenges, which when you look to outside the galaxy, which one of them is resolution, spatial resolution. It's getting better and better with MUSE, with instruments like that. Then you have a problem of age resolution. You use synthetic models to analyze integrated spectra, but the age resolution is really not good. And then you have what you see is luminosity weighted, which is not a problem we have in the Milky Way. So you see weighted by the luminosity, and you have to convert this in mass weighted. These are all difficult when you are in another galaxy. What are our challenges here? Our challenge for the Milky Way has been volume coverage, because in the beginning the good data was sitting here next to us. Now this is what is changing now. Age precision for stars that are far away, because I can obtain isochron age compared with stellar models, but then I have to go to subgiants, and then they are lower luminosity, and I am nearby, because if I want to go red giants, the stellar tracks are too close to each other, the ages you cannot get. So you get ages only for stuff that are nearby. It is a problem. And we'll show how this changed. And then you have large extinction. We have to peer, you have to go to the bulge. When you see a galaxy from far is something, but when you are inside the disk, trying to understand the bulge is a different thing. So these are different challenges in the different fields, but now we'll get to the point of data where these things are complementary to each other. We can learn a lot from each other. Now, what are the advantages? So in the case of there, of course, you have a volume coverage for free, and you have a diversity of galaxies. You can study elliptical, spirals of different kinds, with bar, without bar. We don't have that. And you have this multi-wavelength information, maps in multi-wavelength information. Well, here we have several advantages, and that's why I like this field, because we have now the chemical properties of individual stars, we have ages for individual stars, we have the kinematics for individual stars. That's important because we're going to compute orbits. You know, that's key. And we have multidimensional tracers. We have 3 positions, 3 velocities, and a multitude of chemical elements, depend on your spectral resolution, depend where the star is, far or nearby. So we are going to use concepts of chemical evolution here. I have put here some chemical evolution, is just what I've been talking until now, okay? And these are some reviews that are interesting, that have come out. So there are different models of these lines that you saw are chemical evolution models. There are different families of models. I'm not going to go into this because I'm going to dive into the data soon. But this is just the beginning of the story. You have to know that there are simple analytical models, and you can look to the review of Francesca Matteucci, where she talked about those. They are useful when you are analyzing data at high redshift and you want some first idea of what's going on. Then you have numerical models where we're not going to assume instantaneous recycling approximation. What is instantaneous recycling approximation? Is something that do not take into account the time scale I told you. You assume that as soon as the star is born, it releases. Is valid only for massive stars, as I show you. So if you're working with oxygen, fine. But if you're working with iron, not fine. So models, then you need numerical models. That's the kind of models I did my PhD on. Instantaneous recycling approximation is giving, but we still use instantaneous mixing. What is instantaneous mixing? Once the stars die, whatever with their time scale, mix. So you do not have an homogeneity in the interstellar medium. It's supported by data nearby, but it's not valid in the early universe. So that's also something. Then you have the same as above, but you relax instantaneous mixing. You assume inhomogeneities. That means different volumes sample the IMF in different ways. So here, 100 solar mass die, there, a 50 die. And the volumes are unmixed. So you see this inhomogeneity. So that's why, and you learn a lot when you have good data from the scatter in the abundance ratios now. Not only the trends, the scatter gives you amazing, and this is something very modern because only now you can trust your error bar so that you can see that the scatter is real, right? So that's amazing. Then you have chemodynamical models. They are needed now that put together the chemistry plus the dynamics because as I told you, stars are punched from here to there. And they lose some information in angular momentum. There's a change in angular momentum. So you can find a star here nearby us in a circular orbit behaving like a thin disk star, which is not from here. And how can you tell this? This is what we're going to learn. And then you have cosmological simulations with chemistry. This is difficulty because you have a problem how to model star formation. This is one of the big feedback and all that. Then you can have simulations in the cosmological context. This is key because what? Because our galaxy had been hit several times by other things. And in the cosmological models, you have the possibility to see what happens when you have a merger. So why I'm showing you this list? Because we are in the field in a moment where you need all the different approaches to keep on going. Because the cosmological simulation cannot give you the grand truth. Because you do not forming how you form stars, how you have the feedback, and so these are all 3 parameters there. But you know a lot of the effect of these 3 parameters if I run a chemical evolution model. So the approaches have to go hand in hand. Okay? So as I said, I will focus on long-lived stars here. They are going to be our fossil records. That's why it's called galactic archaeology. Our fossils that's telling the story of the Milky Way are in the oldest stars, not the old stars, in the stars that have lifetimes longer than the ones that stayed, okay? The lifetime longer than the age of the universe. And when I go far away, I have to go to the red giant branch because they are bright. And they have a very big baseline of age as well. This is the HR diagram. So with that, we can learn about, we are going to use the stars that have lifetimes spanning the whole galaxy history. Most of them with chemical abundance from the gas from which they were formed. This is key. The star formed and didn't change its composition. Most of them, there are some that change, of course. They don't change its composition. So now, if this star was formed in the bulge and was kicked here, I can tell how from its chemical position or chemical position age together. You see, when things start not fitting, you see that that's the, so it's very important. This is why it's fossil record, because the star keeps the chemistry from when it was born. Some were born 13 giga-years ago. So you have the chemical composition without going at high redshift with JWST. So we can then translate the sky view into real positions and velocities, and we call this 6D phase space information. That's what is possible with Gaia, and we are going to use it. So we're going to compute the energy, angular momentum, eccentricity, Z max in the orbit, how high from the orbit of the midplane the star goes. Not using the position Z, I'm using Z max, because the star is moving. So this gives me much more constraint in what I'm going to see. Apocentric and pericentric. The star has an orbit, close, far. I can have these values, and this gives me a lot of information. And this is Gaia giving me. We can trace past merger events by using this phase space plus chemistry. We can trace the galactic populations back in time using the chemical clocks I show you. We can trace the inside formation of our galaxy by studying chemical gradients in the galaxy disk. We can observe the secular process happening, the radial migration. This is so beautiful. And we can see the disk flaring and warp. Amazing. We can compare the old Milky Way to what we see at high redshift with other bulges when we are in the bulge. We can compare the present Milky Way with the local volume galaxy and understand about thick disk. We can obtain, to constrain the different nucleosynthetic sites. Let's say I have a model that is explaining several chemical elements, and there is one for which we are not sure who produces elements. And capture elements. Are they producing type 2 supernova or neutron mergers that give you gravitational waves? So this is all things we can have a say. We can add constraints on the nature of the first stars. As I told you, when we go towards metallicity, we are reaching the first stars. So the first stars that were exploding just after reionization of the universe. And so on and so off. And that's why I like a lot this field. And I hope we're going to have a lot of fun. So we are going to do galactic archaeology. We're going to discuss this. So what is galactic archaeology? It strives to reconstruct the past history of the Milky Way from the present day kinematical and chemical formation. Why is it challenged? You now know, because we have a complex mix of population with overlaps in several parameters, and we also were up to now having a map of a small volume. And why is even more challenging the bulge? Because in the bulge we have large distance, large extinction, maximum mix of populations. And so there is a list of reviews of the last years. The last years is after Gaia is like ramping up in a velocity that's being really crazy. We have one with Beatrice Barbouille on the bulge, and that's amazing because the review was written in 2017, so it came out in 2018. It was just before Gaia and Apogee, which were the two things that revolutionized the whole thing. So like you read everything that was happening until there, and now you need another review completely. And then I will just finish this, and we're gonna pick up, I guess, in the next lecture. I don't know if I have more time. More 10 minutes, so that we can go. So we have then we now know the challenge. We now know what we want to do. We now know what we can do. So now 3 things have happened since 2010. By the way, I was here in 2012, where we had the Sloan meeting here. I think it was 2012. So all these that I'm saying happened after that, and it's amazing. So 3 things that I call the 3 revolutions in the field. One, and I haven't talked about this yet, it's called asteroseismology of red giants. Asteroseismology of red giants, we're going to see it. And this gives, why is this key for galactic archaeology? Because it's key for several other things, several planets were discovered with seismology, so on and so forth. But what is important here is that in 2009, it was discovered that seismology was also, the solar-like oscillations you see in the sun were happening also in red giants. And that gives you a mass and a radius for free. Now imagine you have the mass and the radius of a giant. You get the distance, right? You have the age. It's a model-dependent age, but it's not an isochrone age. So now I can date stars that are far away, which for galactic archaeology is key. So I have good age, good distance, good ages. Is only in pencil beams where the people were looking into this disaster seismology principles looking for planets, that's where we are going to use these 4 ages for these red giants. Second revolution is Gaia, of course, and that's most of it. What is Gaia? It's more precise than Hipparchus and covers a much larger volume. Hipparchus was the first astrometric, which is giving you parallax and proper motion mission. And Gaia goes down to magnitude 20, is really very faint. Most of what I'm going to show you is down to 18. We're not going to, we have a whole bunch of things to explore. We're just in the beginning. And it's a 1.7 billion targets. So, and you have good information for at least 1 billion. And this is obliging us to work in a different way. When I started my PhD, and we had, which was in 95, I think, and we had a good plot of data. We had, I don't know, 100 stars in the plot. You know? So, Gaia gives you, as I said, parallax proper motions. With that, you're going to compute the distance. Essentially, if you invert 1 over parallax, you have a distance, in principle. But it's not going to work. It's work only very nearby. And if there is no extinction. If you want to use Gaia to map, you're going to need complementary information. What's complementary information? Is spectroscopy and photometry in other bands. And this spectroscopy is giving us a lot of trouble because we have to organize the community to go and follow up spectroscopically the Gaia data, but you cannot follow up 1.7 billion stars. You have to pick up the best stars to follow up. No? And we are going to do this with Foremost, for example, or with. I was the project science of Foremost in the very beginning, and now I'm PI of the cover of Bulge and Disk with Foremost, low resolution spectrograph. So we're going to show this. So what we need to work with complementary data, this is photometry spectroscopy, from where we're going to get what? Radio velocities, key to compute the orbits, and chemistry. And then you're going to have the famous 6D phase space information plus chemistry. And the third revolution is one of the spectral surveys, which is called Apogee. Why? Because Apogee was a high-resolution spectrograph, 20,000, in the near-infrared. And with Apogee, we could have for the first time a view on the bulge and very close to the galactic midplane. And this has opened a completely view. So I will finish just with these maps. So here you have a picture of the Milky Way. In the review I have with Beatrice, most of the surveys, spectroscopy were some surveys in the bulge, in the Badas window. And then we had the squares, not on scale, because it's 3 kiloparsec 30, but you have the several spectroscopic surveys, most of them around us. And now we're going to set up for a big change in spectroscopic survey in the galaxy, where we're going to increase the volume. And you still have Plato coming. So in the next, I think, if I have 5 minutes, I'll go for this first revolution, which is Gaia, which is seismology, and then next lecture we can pass to the second and third. So the first revolution is the astroseismology, as I told you. What is this? This is very high precision photometry of a star, and you see the variation in the bright of the star. And if you put into a different way to see this, which is like the frequency of this variation, you cannot learn this now, and you don't need to. You just need to know that when this is a spectral of variation of the light in the stars, which you get from Corot, Kepler, all these missions. And then you can obtain from these spectral frequencies 2 parameters. You can do better with other kinds of seismology, but you can obtain the W max and the delta nu parameters. And these parameters don't need even to know what they are, but what is important is that correlate with mass and radius. For me, that do galactic archaeology. So I work with people that do this kind of thing. And we have, in 2016, put the community together with especially Andrea Emilio, who is working a lot into this area, to use this tool for galactic archaeology. What does it mean? This is the mid-plane here, the height from the mid-plane, and the radius from 4 in the inner galaxy up to 14. And these lines you see is the different pencil beams for which you have seismology. So in these pencil beams, in these directions, we're going to get ages. we're going to get distance. Very good. So there will work as a calibrators for everything we're going to get from other ways, especially for Gaia. So we have organized a meeting about this. This is a dedicated volume that I have edited. And there you have a lot of information how this happened. There is a very nice historical paper we wrote here with Arlette Noels and Josefina Montalban on the history of how this came to be since the discovery that the red giants could give you this sort of information. And then we had to very quickly put together the spectroscopic surveys that were going to follow up those targets, because once you have spectroscopy, you can then get better information. And why is this important? Here you have a plot of distance distance that you get from seismology compared to for example, eclipsing binaries for which you have very good distance. And this is the sort of one-to-one relation you get. So there's a very high precision. The distance are precise to, you get masses of precision of 10%, radius precise to 3%. Into this beam, some of these stars are far away, but doesn't matter. And these are the three missions, how they cover the distance. You see here distance, you see most of the missions cover around up to 4 kiloparsec, most of the data from us. Imagine 4 kiloparsec from us, this is where they are going. And you have this kind of precision age, but that's the most important thing. From this precision mass, you get more or less 20 to 30% precision in ages, which is amazing, because if you are in the red giant branch, your error in ages is 100%. So, and why you get this? Because for giants, you have a very more simple relation between age and mass. This is here for some data, and here is some clusters for which you have ages. And it's a more or less this kind of relation, mass to the minus 3.2. Of course, depends on metallicity. And that's why it's so important to follow up spectroscopically the seismic targets. So just to give you an idea, Corot had two fields. So you are in the sun here, galactic center. One field going out from the galactic center, out from the disk, but towards the inner direction. One field to go into the outer disk. We organized that the apogee would follow up this, you see. This is a vision from ZX, here's a vision X and Y, so like if you're looking the galaxy from above, you see where these fields are going. And that means in this region we're going to have good age and good distance. And that's what's going to help us to see that some of these stars have migrated, which I'm going to show you in the second lecture. So this is only indispensable. Imagine if you had this for the whole galaxy. Here is dispensable beams again, so this is this was Corot that I show you. This red one is Kepler. And all of this, Kepler broke at some point and could not come out from the ecliptic anymore and start doing several directions in the disk. And that's several fields for which we're now going to have interesting information. Is called K2. So when I say K2, is Kepler broken, essentially. So I will finish with this transparency. Seismology of red giants had also a major impact in galactic archaeology, so not only Gaia. And the reason is that it can give me precise distance out to 50 kiloparsec. If I have a spectroscopic follow-up, I can put the different surveys at the same scale, that's also important, of temperature, because it gives me also precise log G, and this, which is the gravity that I can get from spectroscopy, but a factor of 10 better than spectroscopy. And we use this, for example, for wave, and can give me, as I said, ages for stars that are far away. So this has opened also the possibility to study very old field stars where we got age in the halo, and they were from Gaia Enceladus, and doing not only this two-parameter astroseismology I show you, but going to a different level of seismology when you have very good light curves, which is currently available only for Kepler. We could achieve a situation to 11% precision here in this paper that we published, where we could date some stars from Gaia Enceladus, this galaxy that came and hit us, to the level of 10%. So that was amazing. Okay, I will let the Gaia thing for the second part. So here is IAO Symposium organized in Potsdam in July 2017. And here we were like, the data release of Gaia, the big one, which was data release 2, was in 2018. So here we are in a symposium organizing what I'm going to do how we're going to do when we have 1.7 billion stars, how we're going to get ready for that. So we had 2 panel discussion tables. Here you see Josh, Blanta Halton, Beatrice Barbui, for example, Andrea Emilio here, Brigitte Nordstrom, and Anthony Brown, which is the how can I say, the DPAC, so the coordination of Gaia, was coordinated this, that was a more galactic thing, and this was another panel to discuss how we're gonna use these simulations to compare with the data that we're gonna have, so cosmological simulations, chemical evolution, so on, how we're gonna do that. So here you see Francesca Matteucci, Ken Freeman, Julio Navarro, Françoise Combs, and Wise, for example. This was a very rich discussion, like, what's going to happen when we have this data? What are we going to do first? How are we going to prepare for that? How are we going to prepare the spectroscopic surveys? And that's what we did, and that's what I'm going to show you in the next thing. And that's the time also where we wrote this review. That's the last two lectures. You're going to see how these things have changed since that review. But it's used to look at the review. And I also have, if you look to Cristina in ADS, you'll find a presentation of a review I gave in Pucon on the bulge. After that, a lot has changed, so I'm going to pick up from there. And then next time in the lecture, we go to Gaia as the second revolution, okay? And then you're going to start seeing the maps that we have for the galaxy. Thank you.
So thank you very much, Cristina, for this very nice talk. So questions? We have time for a few questions.
Thank you for this amazing lecture, Cristina. And you mentioned that observation and models had to go hand in hand. And you have shown us a lot of new data coming in astrometry, seismology, spectroscopy, everything, and we have to learn how to handle with all this data. So with all this data in hand, what are the main challenges to the models?
Yeah, so that's a very good question, and that's exactly the point I want you to have when I finish the lectures, because you are, it's been very hard these last years because you have so much data, but still you lack a lot of data. And it's always the case. But here is really you have to push you have to use this data in a very short time scale, because it's our generation that have to already start preparing the next. For example, I can tell you we are working on a proposal for Gaia near infrared. For example, one of the Gaia near infrared to fly into, if everything goes well, if we are accepted at ESA and so on, which is a whole big process, to fly in 2045. So I'm not doing this for me, I'm doing this for you guys. And so what is, for example, one of the things that's missing is that Gaia cannot see when you are in high extinction. So you will see, one example I want to give you is when we use Apogee to push, to learn about the bulge. For the first time, in the paper of my PhD student, which was Ana Queiroz from Brazil, she used a sample in Apogee. So Apogee has 500,000 stars. But when you want to talk about the bulge region, we got the good 8,000 stars that are really confined to the bulge, for which we could, for the first time, understand in orbital space. It's very important, because in the bulge you have everything. You have inner thick disk, inner thin disk, bar, and maybe an old bulge. But you just cannot see because they are all mixed. So this kind of data is, and when we did this, we needed parallax and proper motions. And then we were using Apogee. And so by the time we cross-match Apogee with Gaia, we got a hole in between. And this hole is like when you are very close to the galaxy, close to mid-plane and inner, you lost a piece because there is no Gaia. So for some objects you have Apogee and do not have Gaia. So for example, this is like you use up to the point to show that you need something else there because you have so much information already with Gaia. So you need to leverage that data, and you need extra information, so you can show the next thing. So that's one example where you need more data. You need a Gaia, And you cannot launch this new Gaia now. It's gonna go Gaia near infrared because it's the same as Gaia, but it has to do also in a near infrared. But it has to also do exactly what Gaia does, because if you use the timeline of 20 years, the proper motions of Gaia will be much more precise. And with that, you do another jump. But to show this jump, you have to come up to the meat. I mean, what have you shown with the Gaia now, and what is missing? And that's what we're going to see, how it's missing. So for the seismology, we did a lot, but we are always restricted to these beings, and we see that a lot of the data good were very close by. So when I do the gradients as a function of time and show with seismology that how this is being impacted by radial migration, I can essentially only say things up to 4 kiloparsecs. So from 4 to 0, I have 0 information. You see? And so that's one of the cases when you are in the disk. So for each, and the master of the field now is to combine this information and depend on your question. So what are you interested? Are you interested in understanding the end of the gradient, the linear gradient up to 4 kiloparsec, and what's happening between 4 and 0? What data can you use? Well, you're going to have to use Gaia plus Apogee, and you miss the inner part. And that can create trouble. So you really have to master the seismology, the spectroscopy, and the Gaia, and then, depending on your question, you can really advance. Can give you an example. In the bulge is amazing, because I can use a star that came from the bulge. I have a whole bunch of information up to the end capture elements, but I have it here. And then I say, okay, this star came from the bulge. Does it make sense? Then I have to understand what I see in the bulge. And I see, for example, in the bulge, I see that there is an enormous reservoir of stars that have more than 0.2, 0.3 dex in iron. These stars are not everywhere. They are only found there. And then there are some here. They came from there. So then I can use another kind of data. What is the data? I can use other data sets that are not so close to the midplane, but they are up. I see the bulge not so much interfered by the disk. And this is very recent as well. And so that's why it's always missing data, because we are having patchy views, as you're going to see. But it's enormous compared to what we had 10 years ago. 10 years ago, we had what I show you. A couple of surveys there in the Baldus window. Some surveys here around us, 2 kiloparsec. And now, for the first time, we are extending this over the galaxy, right? But we are still seeing that we lack, for example, and that's why I'm covering with foremost, we lack a total part of the south. So between inner disk and bulge, we have almost nothing. Because Rave was too bright, stay nearby. Galah was too bright, stay nearby. Lamost was not bright, but was in the north. Didn't miss the bulge. And so on. And so there you see. And that's how we have along the years find the niche. Where we're going to need, because Gaia you have. And you have to use that data. This is amazing data. And if you have radial velocity, you already change everything how you can work. I had one data set where I had radial velocity for Segway stars. Segway is low resolution. But just because we had radial velocity, we could trace Sagittarius streams nearby and find ages for the first time for some of them, because they are nearby subgiants. I got ages. You see, so that's why it's just to do. I mean, you have the question and you sit on the data and you'll see who can do the what, and quickly you are done. It's beautiful. It's beautiful.
Quick question. You mentioned the importance of knowing the ages of these stars and the precision of the astroseismology, but the astroseismology is still limited to these beams where you have this data. So what is currently the best method to give ages for a large volume of data like Gaia, for example?
Yeah. So ages is the tendão de Achilles, né? Because even with seismology, in the beams, I'm using the initial mass of the star. If a star had mass accretion, it changes mass, the age is wrong. And this is, I'm going to show you, this is what we call young alpha reach. We figured them out, we can see them. So this is already a problem for seismology, but it affects around 30% of the stars. 10 to 30% maybe. So that's another thing we are. So how can I improve from that? So up to 2 kiloparsecs, I can go with subgiants. Beyond that, I would need the seismology to bring me some age. I had a 10-year, is this going to be, is this recorded, right? I had a 10-year discussion with the Plato people to also do the giants, because the Plata has a huge field, you know, and now we got some giants but very few. But can you imagine you could use the Plato fields, which are bigger, to do also the giants for small? Then you could do a lot. But okay, you're not going to have that, it's clear now. So now the next step is the large telescopes. So ELT, with instruments like Mosaic or other instruments, Andes and so on, especially Mosaic because you can go far away. So the ELT, and now there's another project called WST, which want to build up a whole big telescope again. And what's the goal there? The goal is to go to the subgiant regime using large mirror. And then you can do what I'm doing for 1-2 kiloparsec, you can extend. And by the Gaia data release 4 and 5, you're gonna have, I mean, you can do beautiful isochronates. That's why it's needed much work in stellar models, which is something that people take for granted. Now we know stellar evolution, a lot of money go in other things. The backbone of the whole thing will be stellar models. So precise, very good stellar models, using a lot of seismology for understanding stellar models nearby. So convection, mixing, and so on and so forth. And then on the top of more good stellar models, have good stellar tracks, taking into account rotation, for example, very important. And then when you have the big telescopes, you're gonna go down to the subgiant branch, subgiants, and main sequence turn off, and you're gonna have H's. Yeah, that would be amazing.
Thank you.
Okay, so we are a bit late and we have to go to the coffee break. So let's thank Cristina again, please.